Welcome everybody. I hope everyone's had a good time at Devox Morocco so far. I'm David Blevins, and I'm part of a company called Tommy Tribe. And we do a lot of stuff with middleware, specifically Apache Tommy, but we rolled out a pretty big install of Tommy a few years ago, and we had a customer ask us, so now what do we do to secure this thing? And then we're like, that's a really good question. A lot of app servers out there support only basic auth, and so there's a huge gap to where everybody kind of is and where everyone needs to be. And so I did a lot of research. We even asked like Microsoft and Google and Amazon, and having participated in the standards on the Java side for a very long time, I know that there's always somebody who doesn't like what's being developed in the standard and eventually leaves. So one of the things that we did, aside from just reading the specifications, is go look at the names on the specification at the first version and look at the names now, see who's not on the spec, go ask them what they think, and then they can't stop telling you all this very useful information that you're never going to read anywhere else. Of course, it's always over the top, which is why you have to keep asking everybody, but we went up with some really good kind of net takes. And I really felt that I wanted to put together a talk on security to try and express some of those hard-earned learnings. Because I think that there's like, you almost never see talks on security. You're seeing them more these days, but I feel like there's almost like two people who do talks on security. One who are completely over the top into security and they can't speak human, and then people who are too afraid to do talks on security who don't do talks on security. So I was trying to be the middle one. So we'll see how well that parts out. But I think one of the things that kind of captures the state of things these days is this quote, which is, the nice thing about standards is there's so many to choose from. And that's really what you notice first off when you try to study REST security, is that you find specification A, which promises like the sun and the moon, gets partway in, and then there's nothing but references to other specifications that you haven't read yet. So now you go read those, and they also get partway into what they promise, and they point to this specification over here, and you start reading that, and then it points to that specification over there, and before you know it, you've got a circular reference, and you haven't figured out the whole world yet. And you're like, I can't even fathom what this is. The other thing is that specifications are almost inevitably filled with an extreme number of options. And every time you add options extensions, you get less of a standard and more of a, well, I guess anything goes. And then less is being specified rather than more. So in this talk, I tried to show a very narrow set of options, the ones that are most practical and the most usable. And the other thing that's kind of very frustrating about standards and these security specifications is that they tend to rename everything that previously existed, and they almost seem really happy to make simple concepts sound very, very, very complicated by giving them all these big names, and the names all refer to each other, and you almost doubt that you understand it because you're like, well, if it really is just this, why are they calling it that? And then so you doubt yourself, and that doesn't help at all when you're trying to learn these things. So we're going to try and get through this without being very fancy at all in the terminology, showing a reference architecture. So here are the areas that we're going to focus on. So if you look at the industry right now, I happen to notice that there are kind of two styles of security. Most people are doing JSON Web Tokens. That's Google, Facebook, things of that nature. Amazon, however, does not use JSON Web Tokens to secure Amazon EC2 and AWS. They use an approach called message signing, and when you get your little Amazon API key and your API secret, that's actually used to do some digital signatures on the message itself. There's a simplified version of that specification written by someone from Amazon who is now the VP of development at Oracle, and that specification is called HTTP Signatures. So we're going to look at that as well. And we're also going to see how these two things actually could go hand in hand. And so at the end of this talk, you're kind of going to get a this is what everybody's doing perspective, and here's what we could be doing. Okay, so to make things useful, we establish a baseline architecture, and we're going to measure all of the solutions against this baseline architecture. So in our baseline architecture, we're going to say that we have 1,000 users on the other side, and they're each sending 3 transactions per second into our backend. We have a gateway in the middle, which is like an Nginx or a HTTPD or some security gateway or something of that nature. It does the checks, and then it forwards up to the back end. On the back end, we have a microservices architecture. So we're going to assume that there are at least 4 microservices that have to get hit in order to answer our request. All right, so just without any security, plain old traffic, we got 1,000 users, 3 TPS each, that's 3,000 TPS coming into the front. 4 hops being generated from that, so that's 12,000 TPS on the back. That's 15,000 requests total per second. Okay, so that's our basic load. All right. So first we're going to talk about basic auth and its problems, because that's where we're all starting from. And I think it's very helpful to take a look at where we are. So basic auth, we have this incredibly complicated and unbreakable technique called base64 encoding of a username and password. Nobody has ever broken this in the last 20 years of computing. It's never been done. Oh, wait a minute, that happens all the time. So basic auth, they simply take the username, they take a colon, they take the password, they base64 encode that, and they stick that right in the message. So obviously if you see the message, you get the username and password. It's very unsecure in that regard, and so people start to ask the questions of how can I improve this? But I think it really is important to see how this thing pans out architecturally so we can measure its replacements against basic auth. So if we have 1,000 users on the other side and they're sending their 3 TPS, we have 3,000 username and passwords per second being sent at the gateway. That's a lot of exposure of secrets, all right? So there's a lot of things that are inherently secret that are being transmitted on the internet to us, and that opens us up to all sorts of vulnerabilities right there. We're going to have to do 3,000 TPS against our username and password store, which in most cases is like an LDAP or an Active Directory of some kind, perhaps a database. So our database or our LDAP is doing 3,000 transactions per second. It has to equal the number of incoming transactions that we have. Okay, and then on the back end, we typically find ourselves with no authentication at all. Who secures the back end with anything other than IP whitelisting? 2, maybe a third. So not too many. And that's actually a pretty big problem because the people who are on the outside we perceive as the dangerous ones, but the consultants we let inside our enterprises, they're technical, they're temporary, and they're exposed to all of our systems all the time. There was a famous company in the United States called Target, and they got hacked and lost so many credit card numbers, and the hack was basically someone who had once upon a time access to the inside of the company, and then from the outside broke in and grabbed all the stuff because they knew how everything worked. But they were basically someone from the inside. It was an inside job, as they say in spy movies. Or movies that involve casinos and people doing acrobatics. Okay, if you do decide to secure the back end, now you're not just going to have, and you send that username and password to each microservice, and each microservice does a security check against LDAP or your database. Now you're not just doing 3,000 transactions per second against LDAP, you're doing 15,000 transactions per second. So it is not very scalable, and so people generally don't do this, so they do IP whitelisting. IP whitelisting is the natural enemy to elasticity. You have a bunch of hard-coded IP addresses that you give to a network administrator that sets up network rules from them, commits that stuff to some source repository, we hope, and then reboots all the network equipment, and now you have really hard-coded routes between different servers. Well, if you're hoping to go elastic at some point and boot up a bunch of machines and shrink them down, you will have new IPs all the time. You can't possibly be emailing your administrator all the time. I mean, you'd have to have like a whole team of network people, real time, typing in stuff like that. It's obviously not even realistic. So IP whitelisting is what most of us are doing, and it's one of the first things we realize do not work in an elastic world. And so as long as we're going to solve security correctly, let's solve this problem too. So the third thing that is really, really terrible about this kind of architecture is that if microservice A over on this side says to microservice D over on this side, hey, give me all of Joe's salary information. And that microservice says, sure, go ahead and have it. Well, that's an obvious problem. Someone on the back end can just be sitting there downloading all sorts of salary information from anybody at any given time, and there's no proof that Joe approved this. So that is also a big problem. Okay, now let's assume that the evil country of Latveria attacks. So Latveria, who knows where Latveria is in the globe? No Marvel Universe fans in here? So Latveria is a made-up country in Marvel Comics. It's where Dr. Doom is from. Anyway, so Dr. Doom gets his evil minions and try to attack us. And so we have 6,000 transactions per second coming from the evil country of Latveria. And so now we have 9,000 transactions per second going against LDAP. So they're effectively easily able to denial of service us on our security layer. It's inherently a big problem. Okay, OAuth 2 is the next iteration of security that people talk about with REST security, and it does have some good things, but we have to understand very, 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 very carefully there are two kinds of OAuth 2. There's OAuth 2, like in the way it was first done in the first 5 years of OAuth 2, then OAuth 2 post JSON web tokens. They're not even close to the same thing. So if you're saying we're using OAuth 2, check we're safe, you should understand why it is maybe you've made a bad choice. So it's not just, you have to understand more than that. So first of all, I'll break down what OAuth 2 is generally, okay? So OAuth 2 generally is that per person or per identity, you don't just have one username and password. You have potentially many little tokens associated with that person, and those tokens are associated with the device that was used to log in as that person. So if you lose your phone, all we have to do is, hold on, keyboard, yep. So if you lose your phone, all we have to do is just scratch out the token associated with that phone. We don't have to log you out of everything that you have. So it's definitely an improvement, right? But on the wire level, it is not looking very innovative. So to get an OAuth 2 token, you basically post via form URL encoding a username and password to an endpoint. You get back a response which gives you at the bottom there a little access token and a refresh token. And of course, this is not called logging in. This is called granting, which is so awesome. This feels very innovative. I bet you nobody in here has ever done form URL encoded login from a website ever in your lives. Probably you're doing it every day and have been doing it for the last 15 years or so, because a basic form on a page is form URL login. It's got a user box and a password box, and when you hit it, it looks exactly like this going over a wire. The awesome thing is this is like 30 pages into the OAuth 2 specification. That's how much they make you read before they show you what you already know and call it something completely different, which is one of the frustrating things about standards. So far we haven't really done anything very innovative. We've got our access token and refresh token, and when we want to actually send a secured request using this access token, we put it in a header called bearer. So the prefix is not basic as it was before, it's now bearer. And that string that we have in there is not necessarily base64 encoded. It is whatever the OAuth 2 server wants to make. For all the stuff in the first 5 years, they look this short, and they're effectively pointers, right? And so we send our requests, and we can do all sorts of different kind of REST requests, and as long as we keep that access token in there, we're going to keep getting approved until eventually, bam, we get a 401. Now what happened? Well, a very core concept to OAuth is that we have to expire these tokens at a very aggressive rate because they're secrets, and they're no safer than a password. And so now we're exchanging these things quickly. So we send our refresh token, and we do what's called a refresh grant. This one doesn't involve the user logging in again, typing the username and password. We just take that token that we got at the first time, and we send it back to the OAuth 2 server, and now we get a new access token, refresh token pair. So now we at least have passwords with entropy. So that's pretty good. It's starting to sound very promising. And so we can go ahead and throw away the old access token, refresh token pair, use the new access token, and then continue. All right? So what have we achieved with this approach? Well, we have a lot more passwords. That's effectively what we achieved. Or at least our devices have more passwords. If someone sees your access token, just like they see your username and password base64 encoded, they can use it to be you and log in as you. So it is actually no more secure than a password. And in fact, there's a lot more of them. And so this is where the funny thing is like, you know, we've renamed tons and tons of things by now. If a vendor walked into you and, you know, into your company and you said to them, you know, we're trying to get rid of our password-based system. What's our solution? And they said, I got an idea, more passwords. You'd be like, get out. But if they said, access tokens, you're like, what's an access token? Oh, it's better, it's more secure, and they'll just say all sorts of buzzwords which are from the specification. You'll be utterly confused, not understanding that you really just bought more passwords. And you'll roll it out and you go, this thing doesn't scale very well, I have problems with it, and you'll wonder why, and it's just because it's basically the same thing you've been doing for the last several years. So the frustrating, you know, term alert, grants, when you see the word grants in the OAuth 2 specification, they really mean logging in, but they don't call it logging in because, you know, you get paid by the new concept as a security spec developer. And so, you know, that's a boat right there. And then the other one is, you know, token. What the heck is a token, right? I like to refer them as slightly less crappy password, but equally crappy session ID. Because effectively, if you log in with a form URL encoded, username and password, and you get back an ID that you have to send all requests, is that any different than form logging in and getting a session ID back that you send every request? Guess what? It's exactly the same. So in this regard, OAuth 2 in this style is no different than a standard HTTP session. It's just now the HTTP session ID rotates once in a while. Do you need 50 pages of specification to say that? You could probably just say it's like that other thing, but rotate the session ID, and people are like, yeah, it feels like kind of a lateral move. But we put a whole bunch of words on it, we publish it out, we make products, we market, and everyone is like, this thing is awesome. So, not surprisingly, what this looks like on the back end is instead of 1,000 people hitting LDAP for 3,000 transactions per second all day, they will, we'll say for the sake of the presentation, they're all going to do the grant, aka the login, once a day. The access token, refresh tokens will rotate every half an hour until the end of the day, and then we don't allow them to keep refreshing anymore. They have to go back and log in again. Their session has expired. So effectively, they have an HTTP session that lasts one day. So LDAP gets hit 1,000 times a day. That's a great improvement. But now we have a token store on the back end that's still getting hit 3,000 transactions per second. So now we've moved our scalability issue from here to there. And now we have 2 points of failure because LDAP is still a point of failure at some regard, and our token store is a point of failure. Okay, now, does this improve our ability to secure the back end? Well, if you pass this weird-looking string that only the OAuth server knows about from microservice to microservice, microservice A says, who the heck is this? And microservice D says, I have no idea. Let's ask the token server. And of course, so then they all go flooding back, and now our 4,000 transactions per second off the back end, each of them forks off a request to the token server to ask, what does this token mean? At which point, the token server now is getting 55% of all traffic of our whole enterprise, and it bursts into flame and promptly dies, and now we're getting no transactions per second, because this is what happens when you have center points of failure. When all of your users and all of your microservices are all calling this for every one request, I mean, that's a really bad architecture. So, not surprisingly, this has the same scalability problems as standard sessions. Worse over is that if you want to be able to determine what that string was, so you want to be able to answer this question 5 years in the future, you have to keep that token for 5 years. So that means that store, which starts out at 1,000, then 2,000, then 1,000,000, then 3 million in 5 years is 20 million and 50 million, and the time it takes to check tokens becomes slower and slower. It becomes heavier and heavier, and it becomes more expensive to maintain. You got to keep scaling it out, which is a really awesome business if you're a security vendor that sells by the core. It's a terrible thing for you guys, though. So, what is better than this? So first of all, now that we see how this thing works, let's try and come up with some better names for access token. Maybe we'll call it access pointer. Not very sexy, but more honest. We can call it access primary key. That is spot on, because that's exactly what it is. If you called it access primary key, people would think it would be not that fantastic to roll out into their enterprise. But that's actually what it is. OAuth, let's give this a better name. I like to call it high frequency password exchange algorithm, because that's kind of what it is. It's just exchanging passwords at a really, really fast rate. There's another frustrating thing about OAuth is that refresh token concept, totally optional. So what happens if you take the refresh concept away and you have just the session ID that lives forever? Now it's less secure than an HTTP session, because at least an HTTP session has a time to live on it. And I have encountered OAuth and products that do not support refresh tokens, or they support the same refresh token living forever, in which case if that thing gets stolen, I mean, that's a huge problem. So that's one of the frustrating things, is that the spec had one job: to improve something a little bit. We discussed that the improvement is that at least it can rotate these things, but even that's optional and you frequently don't find it. Well, I mean, this is a lot of expense for very little. All right, so to understand things from here on out, there's just one concept that you need to get, and it's hashing and signing, okay? So I'm gonna pose a problem to you, and we're gonna figure out how to solve it. So we have a directory on our file system, and files are in there, and they may change. And we only want to be notified, we only want to act when the contents of the file has changed. Okay? So, do we monitor those files for changes in the date stamp? Who says date stamp? Okay, if no one raises their hands at the end, when I'm gonna ask again. Do we monitor the files for changes in length? Okay, so no one raised their hands. Who has the right answer? Exactly. I mean, it's right there on the thing. So, hashing is the concept of it's basically magic. It's statistical magic. You take a number, and you take a string of ones and zeros, and when the data comes through, kind of like an abacus, you just shuffle those ones and zeros around, and when the data stops, that number you get is your hash. And so here's a good way to understand it. There's these things that we have in the US and other snowy places. We call them snow globes, and they're like a little snowman inside and little snowflakes, and you shake it up and the snow eventually settles. And then so that kind of concept is very similar to hashing. We have a fixed number of snowflakes in there. Here we have 256 snowflakes, so 256 bits, ones and zeros. And as the data, we stream the data through it, and we basically shuffle those ones and zeros up. And when the data stops, whatever those ones and zeros are in, that's our hash. So we break open the snow globe and we get the hash out, and then that's the number that represents the data. Okay, and you can see the snowman has a little tear because I just broke open the snow globe. Little fun thing. So the more snowflakes, i.e. the more bits, the stronger the hash. So there's barely enough room for the snowman in that one. So SHA-128, aka SHA-1, is something that we used to use, but now is not in use anymore because there's just not enough bits in there. It's easy to replay data over and over and over again and eventually figure out how to have the same ones and zeros and change the data. So we moved on to SHA-256, and at some point that will wear out and we'll go to SHA-512. So basically, bigger snow globes with more snow. So here's an example of how to protect data, right? So say we have this file, and in the file it says Morocco beats Ivory Coast 2-0. By the way, good job. Okay, so the hashes for that exact string with the new line at the end is this in many popular hashing algorithms. Okay, if you hashed that content yourself, you would get those same numbers. Now, Ivory Coast is a little bit mad, so they come in and they try and hack the file and they change 2 to 1, but now our hashes are all different, so we catch them. But then we argue, who has the right hash? Was it their hash or our hash? And now we have to figure out some way to tell who is the truth, who's telling the truth. So effectively, what we need to do is protect that hash. When we make that hash first against the 2 to 0, we got to take that hash and we got to do something with it so that if someone tries to change whatever, we can catch them in it. And so we basically put that hash inside a box and we lock it with an asymmetric key or a symmetric key, and there you have a digital signature. So the resulting thing is basically a bunch of ones and zeros that got put into another bunch of ones and zeros that are encrypted with a encryption mechanisms of choice. The advantage of public-private, which is the little black key and the white key, is the white one is what you use to check and open the box and see what's inside, but the black one is the one you use to close the box, and only the person with the black key can close the box. So the most important thing you have to understand on this slide is we do not distribute the black key widely. Only the referee gets the black key. Once the referee has made the call on the score of the game, he or she signs that thing with the black key, puts it in the back of their pocket, distributes the white key to the whole world, and they can verify that referee's call forever using just that white key. And if someone comes along later and hacks the file, well, doesn't matter. You have the white key, you can check the signature, it doesn't pan out, you know that they're lying. And that's the basic way it goes. Okay, so another thing is people typically look at like GitHub, they have little hashes on there. People really typically think of a hash in the string value. Understand that string value, the ABC, that little hex thing, is just a representation of binary. This is a small note. There's many ways to represent the binary. Who knew that there's such a thing called base 85? Yeah, I had never heard of that one myself. I Googled that. I was like wondering how high can you get? So basically, we see a lot of hex and base 64 as ways to take binary data and make it textual. Base 85 is a popular one, but ultimately there's just ones and zeros. It's a binary number. Okay, so if you understand what I've said so far, You know how to protect strings of data by hashing them and using some sort of public-private key or symmetric key to basically make that thing infinitely protected. That's what everything that's going on with Google and Facebook and Amazon, all based upon signing in some way. So if you get this, all the specifications are syntactic sugar. They're really just dressing up this concept in various ways, but that's the important part. So if you understand nothing else in this presentation than that, you're way ahead of everybody else. Okay, so JSON Web Tokens. They're pronounced JWT. I don't know why. JWT does not spell JWT to me, but maybe I'm not a security spec creator yet. Maybe one day I can make these cool things. I guess the domain JWT was taken or something. Anyway, so JWT, that's the way it's pronounced. It's a fancy JSON map that's signed. That's really all it is. You take the signature, you base64, code a few things, you build in there expiration explicitly. So now instead of OAuth 2 having possibly some expiration, it's built into the token for JSON Web Tokens. And what these do is the JWTs, they replace the access token. So before, we had this as our access token, and now we have this. And this is precisely why we need to show the architecture, because almost everybody in this room thought, well, I want the smaller one. And you don't want the smaller one, right? And there's a very significant reason why. I'll skip this part, but basically the base64 encoded bytes look like this. We have information about the user in a JSON map. We can put what their name is, what their email address is, we can put what permissions they have, various things like that. And then we basically sign that, and that's the blue part of the bottom. We base64 URL encode the signature. You can see it already base64 URL encoded, and the top two parts, and then we get this. So that's effectively what we have. So this has a subtle but very high impact architectural change. Okay, so I'll skip this part. What we can do now is when a user logs into us, they do the grant. Okay, they give us the username and password. We go to LDAP and we scoop out a bunch of information about them. All right, we throw that information into a JSON map. We digitally sign that JSON map with a private key. We keep the private key, but we send that signed map over to the user. And we keep a little pointer to the signed map for the purposes of revocation. Should we want to forcibly log the user out, we just put a little number in there, and then we put that in a database, and then we have just a database of numbers and not much else. Okay? The actual state is then held by the user, and we have pointers on one side and state on the other, which is the exact opposite of what we had before. Before, the user held an access pointer, and the state was on the back end, and we flipped that. Okay, so now when someone logs in, we're going to have them post their username and password just as before, and now the access and refresh token that they get back are bigger. Okay, so we do the whole process, and they send the access token just as they did before. So our messages got a little bit bigger. And what happens at the back end, however, is very significant. When that access token comes in, we do not check a store to see if that token lives in the store. We simply check the token with the public key, and if the signature fails, we don't let them in. We don't even need to check any store at that moment. If the signature doesn't validate, we don't care about anything else. We didn't make it. So we throw that thing away, and we don't even think a second time about it. The only time that we check the store is on the refresh process, which to our presentation is happening once a half an hour per user. So that effectively means we do have a store of pointers, but we're only checking it like, every 30 minutes per user. Mathematically, that store of pointers is getting hit only 0.55 times per second all day. So from 55% to 0.55% at a half an hour refresh. If it was a 1 hour refresh, that store would only get hit 0.27 times per second. So this is a massive improvement in scale because we're effectively now stateless. The majority of calls only get a public key check. We check inside the token for the expiration, and we know the user can't modify the expiration because if they do, the signature doesn't verify because the hash isn't going to verify. Okay? And so now we have ability to put information about the user in the token, to put the expiration in the token, and then when the token comes in, we check it with the public key, and if that passes, we know everything in there is true, and then we look to see if it's expired. If it's expired, we make them do a refresh, and then they get a new token. And so it's a very great system. And now for security in the back end, not only can we use that public key to check the token at the gateway, but we can give that public key to everybody in the back end. So all the microservices can have the public key installed in the Docker image, wherever you want to put it, and then you pass the token along on the back end, and when they see a request come in and that user's token is in there, they also check it with a public key. And if it passes, then it's a valid token and it is that user. And so fundamentally, before, we had the ability to get all of anyone's salary information at any time for any reason just because we happen to be also in the back end. Now, what we can do is if microservice A says to microservice D, give me all of Joe's salary information, and they do not pass any token at all, microservice D should say, no way. Joe is not on the other side. I have no proof that Joe's asking you to do anything. You can't get Joe's information. So you simply pass the token of Joe from A to B or to D, and then D checks that token with the public key, and if it pans out, and that token is actually Joe, it can't be a different user, then you go ahead and give Joe's salary information. So the only way someone from the back end could actually mine information from another system would be to magically fabricate a whole bunch of valid tokens for every single possible user and send them out there, but you have to have the private key. So you need to keep that protected. Okay, so now Latveria attacks again, and we have our same healthy traffic at the top. That's generating our 3,000 TPS, and it is passing the public signature check and going on to the back end. Now we have our 6,000 transactions per second coming in from Latveria. All those fail the public key check, so we drop those tokens on the floor. We don't check the token store at all. There's no reason to do so, and the traffic goes nowhere. So effectively, with this system, unlike OAuth 2 with plain access tokens and basic auth, unhealthy traffic does not have the ability to denial of service us unless they try and just simply saturate our CPU with RSA key checks, but they're pretty light to do, and it's very easy to scale that up. You don't need to have, it's not a persistent disk check, right? It's very easy to scale stuff that happens in CPU and memory. And so we're able to bounce away bad traffic effortlessly with just a simple public key check which happens in memory. And so only the bad people have a bad experience, and the good traffic sees no additional latency or no slowdown at all. Okay? So that's OAuth 2 with JSON web signatures. So what's that? I do not want keyboard shortcuts. I've never found that keyboard shortcut command ever in my life until right now. Isn't that look like a really cool key map of stuff, but that's just the way it goes. Like you find them in the moment where they're completely unnecessary or unwanted, and you have no ability to find it again unless I Google it, I'm guessing, but I won't. So the very significant thing that's happened here, and the best way to think of it, if you want a easy sentence or easy phrase or easy thought to describe these two things to somebody else or remember them, OAuth 2 with the short access key is basically an HTTP session ID as I discussed. JSON Web Tokens are a signed cookie. Then they have all the architectural benefits of a cookie, but it's signed, and so they're also secure. And so how they work out is very much the same. If you have 6 million users, you have 6 million cookies being stored by the users on their mobile device. You don't need to pay for that storage. They're paying for that storage. Scalability. If you suddenly get another 3 million in another day, you have 3 million more pointers in the database. Ooh, big deal. That's not big data, okay? If you had 3 million more big pieces of text you had to store and you were rotating them once an hour, that would be a big data problem. But you don't. You just put them on, it's a signed cookie, you put it on the mobile device and you let it go and you forget about it. And they bring their state in with them. And so you don't have to check them at all. Signed cookie versus HTTP session. OAuth 2 without a JSON Web Token is an HTTP session. OAuth 2 with a JSON Web Token is a signed cookie, is basically HTTP cookies. Okay, so there's a technique that's called message signing. This is the Amazon approach. This approach is not public-private key. This approach is symmetric key. This approach, we do not sign an identity token, we sign the HTTP message itself. Amazon wants to sign the HTTP message itself, so that way, if someone changes the body, it doesn't check out. If someone changes the headers, it doesn't check out. And what they want that for is that if you order 1,000 machines from Amazon, and then you later say, well, that wasn't me, they say, it was your ID, you're responsible for it, and then you say, well, no, actually someone must have hacked my message, and I said 10, and they added a few zeros, and that's why it was 1,000. I didn't say 1,000, somebody else changed that. Is that, nope, the message was signed entirely, body and all. So if any part of the message was changed, the signature doesn't verify, okay? And so that's what Amazon uses it for. And this is a legal term called non-repudiation, which means the other person cannot deny that they did it because there's sufficient proof that they sent all of those things themselves. Okay, so it is, you know, this is a high-level thing. That's the only link to the specification that you will get. So if you're interested in the specification, preemptively take a picture now. I'll also have these slides up available for download at the end of the session, but now is a good time to do it. So this spec is really awesome. It is only like 15 pages, so it's extremely simple and it's extremely easy to implement. And we've rolled this out with people who had their callers on the other side go, we can't possibly do that, that's complicated. And then they read the specification, they go, oh, that's not that complicated. And especially because you can actually implement a client in Bash. It's pretty easy. Okay, so what you do with this thing is everybody individually, every user, has a symmetric key that you have given them. It's been issued by the gateway, and only that other user has it. So this is canonical or identical to AWS, where you get an API key, an API secret. The API key is the thing in the key name, says my key name, and the API secret is the text you use to sign the message. You have to put in the algorithm you use, so the person on the other side can retrace your steps and make the same signature and do the digital signature check. And then you have to list the headers that you signed. So basically, what this algorithm entails is that you go through the HTTP message and you list the headers that you signed, and you make a big long string by taking the header name and the header value in a new line, and you keep doing that for every header that you want to sign, and that becomes the piece of data that you sign. So that is your, we won against the Ivory Coast 2-0 text. Okay? You build that text up by concatenating parts of the message together that you want to protect as the client. Then you sign that with the key that you've been given, and then you put the signature there at the bottom, base64 URL encoded in the authorization header with the key you used and the algorithm you used to sign it. You send that across, and the other person on the other side is going to retrace your steps by looking up your key value from the ID you gave, and then it will sign the message that it got. And if the message signature doesn't pan out, it's either because someone is pretending to be you or someone changed your message in some way. Okay, so with this approach, we have 0 passwords being sent on the wire. Nothing secret is ever hitting the wire. Let's pause and absorb that for a second. OAuth 2, in any form, those access tokens can be stolen and that person can pretend to be you. Base 64 URL encoded passwords, that person can steal the password from the message and pretend to be you. With HTTP messages, signed HTTP messages, ideally you're signing something like the date header, which changes. And so therefore it's going to result in a different hash and a different signature every time. So if someone steals the signature and tries to put it in their message, they wouldn't be able to get anything to go, because that's a whole different message and you're going to get a different hash. And so nothing on the wire is secret. And that's a very, 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 very significant thing. So all of Amazon's business that they're doing, the $1 billion of traffic of all your API calls to Amazon, nothing secret has ever hit the wire. That's very, very important. We have some people who try to use HTTP signatures to secure the back end. So it does give you the ability to do a point-to-point security of one server to another. So server A says only the servers who have this symmetric key can call me, and you give out the key to just the servers that are allowed to call you. This is a healthy way to do elasticity, because effectively that other side, they could spin up a whole bunch of machines. As long as those machines still had the symmetric key, they could still call you. So this is another way to do something which would be like IP whitelisting, but without having to use the IP address as the common agreement between you. You use the symmetric key as the common agreement to you. And you make symmetric keys for every API call that you have, and you give the keys just to the teams or people that you would, on the back end, that you want to be able to call you. This doesn't solve the Joe problem, where we shouldn't give out salary information for anybody but Joe, but it does allow us to secure point-to-point like IP whitelisting, but in an elastic way. So that's a very, very significant thing to note. So, like I say, this doesn't solve this problem. Hey, give me all of Joe's salary information. The key down there in the bottom only identifies that microservice in the gray circle to the microservice in the black circle. It does not identify Joe. And so we don't have any way to identify Joe, and therefore actually using both OAuth 2 and the Amazon style HTTP signatures is a great way to go. It's sort of one of those things where people say, what's better, healthy food or tasty food? It's like, why not both, right? What's better, OAuth 2 and signing the user's identity, or signatures signing the HTTP message? Both. And so that gets us to the next part of this presentation. There's a new specification that's out, and you don't see this thing in the wild. But my hope is that we will. So OAuth 2 with proof of possession is a short, small little twist on combining these two concepts, okay? So what we do is we have a symmetric key that we create, and we put its name inside the OAuth 2 access token. Its name is now a protected piece of data, okay? We give both this key and the access token to the user, and then we make the users sign their messages when they talk to us. And the key that they're supposed to sign their messages with is, the name of it is in the access token. So here was our access token previously. Now here's our access token. So forget what CNF means, because you'll never remember even if I tell you. I have a hard time remembering, but it just basically means condition, right? When you see this access token, do not approve it unless this condition is met. And the condition is that they've signed the message itself with the key ID green1234, okay? And the token type switches from JWT to POP, which is proof of possession, proof that they have the secret key. So we send the same information, the username and password, in a post on the initial login, aka the grant. We get back our access token and our refresh token. Now we have a third thing down there in the bottom, which is a symmetric key encoded in base 64. It's a JSON representation of a symmetric key. It's got a name in it and you know, that kind of thing. There's a little spec for that. Not complicated, despite the fact that the spec is like also 20 pages. For that, I don't know why, but hey. So now what we're doing, there's what a key looks like decoded. So 20 pages of specification to get that, by the way. It's really awesome. You know why it's 20 specifications? There's like the standard 3 pages that include at the beginning of all these specs, and then there's references at the end, and that itself is like 10 pages. So you could really never have a security standard in the OAuth JSON JWT world that's less than 10 pages. Kind of crazy. So if you're ever reading a spec, skip the beginning and just go like to the second chapter, then skip the end. It'll be so much easier for you. Okay, so we send now the OAuth 2 access token in a header. We call it bearer. And then we send the signature in the signature header as before. And orange 1234 is the key ID. And inside that access token is also orange 1234. So if we get a message on the other side that was signed with the key other than 1234, it doesn't matter if the message signature verifies. It wasn't the key that goes with this token, okay? The best way to describe this is basically an OAuth token, a JWT, is a passport without a picture. It has all of your information in it, but no ability for the person holding it up to be proven the person that should be holding that thing up, okay? So all the usages of OAuth 2 and JWT that don't use this additional concept are basically issuing pictureless passports. So in some way, they're far more dangerous than passwords, because if you get someone's password, you just, you know, you can try to be them, but you don't know what you're capable of doing until you access the system. But the OAuth, the JWT has all their information in there. The username, their first name, their last name, the username, their permissions, they're an admin. All these things that they can do in the target system are in the JWT, and therefore, as an attacker, you have all of your work done for you. They've given you the credentials to log in. They've given you all the information about the user and what you can do as a user. Heck, you got it made. If you had the ability to steal a password out of an HTTP message, you have the ability to steal an OAuth 2 token, JWT token out of an HTTP message, so good for you. And so what you would do as an attacker is you would just sit there and wait. Just wait. That token says regular old user, that token's boring, that one says admin. Let's have some fun. And then you go in quietly once and you get all the things that you want, and you're not generating huge amounts of traffic, because a lot of security products make up for failures in the security system by doing network analysis. So they're expecting hordes of people to come with axes and you know, torches and banging on the front door forever until one of them finally gets in. And they go, someone's attacking you. It's like, no kidding. But with this, they can just wait, get the right thing, sneak right in, and do all sorts of things to you, come right back out, and you would have no ability to detect them via regular old network analysis. So this approach is very good. So it's very much as similar as before, but what we're doing now is that when all the traffic comes in from the front, we first check the signature on the token itself. If it's valid, then we go to check the signature of the message itself, and we make sure that they've signed the message with the key that's in the token. If not all of those are true, they can't get in. And we rotate those keys with the refresh token, so if someone hacks and reverse engineers a message long enough to where they're able to figure out your secret and try and make messages as you, well, it's going to change once a half an hour or once an hour, and they're going to have to really, really get on their toes. And so this is like banking level secure, and the people working on this stuff, a lot of them are people in the banking industry. One of the person who works on the proof of possession concept is a guy from the bank called Nomura, which is a huge bank in Japan, and they're global, and this is what they use to secure the most sensitive data. They protect the data, they protect the identity, they link them together, they put a picture on the passport, they rotate that passport every half an hour, and take a new picture every half an hour, and it's really hard to break. So that's all the time that I have. Here is a reference for that. I have also a link for the slides. I'll wait for the people, and keep your cameras out. Okay, we have, you can get the slides for this presentation at that link there, and then of course, we don't know all this for no reason. We actually wrote an API gateway that does all the stuff that you saw, so you can actually sign up for a beta version of that that's up there. And for just the duration of Devoxx Morocco, we have like a special sign-up link that we're going to give like the first 10 people to sign up like a shirt or something like that, and I actually have shirts there, and so that one's going to run for just this week, and we're going to try and find some clever way to like reward Morocco specifically, because I think that would be kind of fun. So anyway, go ahead and go there, and you can get these slides, and if you want to sign up, that's optional, it's not mandatory. So thank you very much, and I hope you had a wonderful time. I think I don't have time for questions, but unless they kick me out. Okay, questions? Go ahead. OpenID is a very specific, so the question was, what's the similarity between like a JSON Web Token and OpenID? OpenID is effectively a very specific flavor of JSON Web Token. So they actually define what the key value pairs are at minimum in the token. And so, you know, that's the short answer. OAuth 2 doesn't define what the token looks like, so JSON Web Token says the token must look at least like this, and OpenID says it must have at least this in it. What's that? Oh, SAML. Okay. So what's the difference between JSON Web Tokens and SAML? So SAML predates JSON Web Tokens by quite a bit. The difference with SAML is that it's very XML based, and all the key value pairs are in XML. The size of a SAML token is like 3 times the size of a JSON Web Token and has roughly the same information in it. And so it's not that a SAML token isn't useful or that style of security was flawed in some way. It fits very well in SOAP. It's meant for SOAP. And it exchanges in SOAP, and all the exchanges have to do with sending the information in the body and the SOAP headers. But it doesn't fit so great for REST because, well, not that it couldn't, but no one put the work into it because they're like, well, we're not dealing with XML anymore. We don't want to put things in SOAP bodies. So they made a world that's simpler but has similar concepts. So SAML and JSON Web Tokens are functionally equivalent, and one can replace the other. And so, you know, the one thing that I would caution is I've seen people use SAML tokens and they send them to like third parties, okay? I don't know why it never became aware in that world, but if that third party has the SAML token, they can come back around the front and the gateway and be that person. I call it the movie ticket problem. So If you go to the movie theater and you give someone a movie ticket and then they go through the turnstile and into the theater, they give the ticket to their friend in the back door of the movie theater, and he leaves and goes to the front with the ticket, goes, look, I have a ticket, can I get in? And you say, okay. Basically, someone who isn't the owner of the ticket can get in. So what you should do is rip the ticket on the way through. So, hello, let me see your ticket, rip it, great. So if they go around and they come back in the front, they get it, well, this is not a ticket for entry. It was already used. And so one of the things that we do is we will sign the JSON Web Token twice. One with the key pair that's only valid for the outside, and one with the key pair that's only valid for the inside. And when the token passes through the gateway, we take the outside one off and send it back in, effectively ripping the ticket. So if you want to use that token as a data token and give it to your third parties, it's safe. But those third parties can't come in the front door. So it is effectively the same as a SAML token, but I believe that we're doing things with JSON Web Tokens that we're not doing with SAML tokens because they're lessons learned over time. And, well, JSON Web Tokens are the latest thing, so we're putting the lessons there. And so they're similar, but I don't believe people are working on SAML anymore. It's just kind of done. Yeah. No, so the question was, when you mix JSON Web Tokens, and by the way, if you need to leave, go ahead. Feel free to grab a shirt on your way out. So we have medium, large, and small. It's okay. So the question was, if we use message signing and OAuth 2 JSON Web Tokens at the same time, is there a security problem distributing the secret keys? The answer is no, because the secret keys are generated and distributed along with the access token, refresh token, and they're seen on the wire once. So they're no less secure than the access token or refresh token itself, and they're also rotated frequently. So the way that the keys are distributed is over the login process. They're not distributed over email or anything other than that, so they're inherently fairly secure. Oh, so in this world, you don't need to synchronize the keys in any sort of static way, only the public key. And so you don't rotate the public key and private key very often. There's really no need to. What's that? Right. So only the public key you install in advance, and the symmetric keys are generated and distributed and rotated, right there as part of the protocol.
I see that we are defining the algorithm to define the request from the client.
Right. So the question was, we see that we're defining the algorithm for signing in the client and respecting it on the server. It is absolutely within the right of the server to reject messages that do not have the algorithm that you want.
Because it was a problem with security, some library used in Node.js for quite a time, and has been fixed several months ago, and it's made it possible for clients to define none as the algorithm.
Yeah. That would be a terrible implementation of HTTP signatures. Yeah. So that's an unfortunate implementation of the library, that it would allow you to say none as the signature algorithm. In our product, we do what's called a security profile, and you specify on the server side what algorithms are okay. And then if they don't come in with that algorithm, you reject it. You can also say the date header can't be more than 10 seconds old, right? And if it's, so then the signature reuse is at max 10 seconds. Sorry, the guy next to you was trying to ask a question. Man-in-the-middle attack. So the only time you could get a man-in-the-middle attack on this approach with signing the messages is if the man-in-the-middle was there at the initial login and the grant process, in which case the man-in-the-middle saw both the username and password and the resulting access token, refresh token, and symmetric key, and they have everything. So there's nothing stopping a man-in-the-middle for a login. But at least that's their only opportunity. From there on out, they can observe the access token, but they can't use it because they don't have the key that went with it.